Welcome everyone to this Access Distinguished Lecture Series. We are privileged to have Dr. Jim Roberts visiting this time. Jim is a very well known researcher in the field of networking, where he is currently working at INRIA, but has a long history at France Telecom in industrial research, and has contributed to teletraffic theory and applied to quality of service and many other fields of networking. Jim has a background in mathematics, both from Great Britain and also with a PhD from University of Paris, and has served in many capacities. He was the co-chair of the Technical Program Committee of Infocom 2003 in San Francisco. So we're looking forward to this talk, which is on information-centric networks, which is a new paradigm for the internet, where you search for contents rather than for individual hosts. So we're looking forward to your talk, Jim. Thanks.
Thank you, Gunnar. Thanks for the introduction, and hello, everyone. So I'm going to talk about caching information-centric network. I've been working in this area for the last couple of years. We have a project in France where we aim to complement the CCN architecture from Van Jacobson by adding different things. But in this context, we're looking in particular at caching and this notion of a memory bandwidth trade-off. One of the motivations for information-centric networking is to economize bandwidth by providing caches within the network. So it's very important. It's a very important design criterion. This is important in CCN. CCN is the Jacobson idea in information-centric network, where initially at least he envisages to have a cache in every router, or at least every CCN-enabled router, and to cache content as it passes so that the next person to ask for the same content will find it locally, or more locally than previously. But the interest of caching is wider than that. In particular, in IP, there's a wide use of caching, particularly by CDNs, content distribution networks, where CDNs like Akamai typically place a large number of caches, a large number of groups of servers at the edge of the network in POPs. Alternative CDNs architectures use more centralized caches, which serve a larger population but use the bandwidth more extensively. And maybe we can envisage, and maybe it exists, in fact, that there are caches arranged in a hierarchy. So this is a fairly general problem, how you can trade off memory in these caches for bandwidth on the network links going up to the cloud. I'm thinking of a network like the network we have in France, France Telecom, where it's a national network and a lot of the content is coming from the world via a tier 1 provider for which we have to pay, and we also have to pay for the bandwidth on the network to bring the content to the users. So key design issues in this area: how big should the caches be? Where should the caches be? How many caches should there be? Depend on this realized memory bandwidth trade-off. And to quantify that memory bandwidth trade-off, we need to be able to evaluate the hit rate, the performance of the cache. What's the probability that a demand for a particular object is satisfied locally or needs to use bandwidth to go across the network? So that's the object of the talk. I'm going to talk about the nature of content retrieval traffic in general, discuss how we can evaluate hit rates under the assumption of least recently used caching replacement policy. Using this model for calculating hit rates, evaluate the cache performance in terms of hit rate versus cache size. And then, in the last chapter, talk about evaluating the memory bandwidth trade-off, putting cost figures in. This last part is very much work in progress, and you'll see that it's not necessarily very polished, but it seems difficult to get a handle on this, yet the issue is essential. So, first of all, the content mix. Looking at the Cisco predictions of traffic in the internet for 2011, it was a prediction when I looked, they claim 96% of traffic is content-oriented, and this traffic is divided into different categories: web, file sharing, video, and video you can divide into user-generated content like YouTube and more video on demand. In the US, at least, is Netflix and Hulu. All TV companies having video demands also. So these are the proportions that you can derive from the Cisco forecasts. The volume of content this represents is typically huge. And the figures I put here are just kind of order of magnitude estimations. The number of web pages is like the number of URLs that Google recognizes, 10 to the 11. The size of each one is fairly small. File sharing, the number of torrents on a typical tracker is typically hundreds of thousands. And the files you share typically are large, or they're very large ones which make the mean is large. And so on the user-generated content and video on demand. These estimates are, as I said, very rough. In particular, the last one is fairly rough. And I showed these figures once in the US, and I was told that this is a blatant underestimation, that the video on demand content is very much bigger than my assumed 1 terabyte, and that it's growing, obviously. But I maintain this because it maintained these figures even despite that criticism, because I don't know any better figures. And in Europe, maybe the video on demand is not so prevalent as it is already in the US. And it's useful to have a different category to the others. It's like 3 orders of magnitude smaller in terms of the total catalog. Yeah.
This number of the number of objects observed over a day, or over what? 10?
No, it's the world. It's the whole thing. Because it's order of magnitude, and well, if I'm a factor of 10 or 100 out, well, I can't guarantee. It's very rough. You know, I've just asked Google how many web pages and things like this. Oh well, okay. That's the way it did. It's very rough. This is a very significant criticism of any work we can do. Yet, I maintain that it's very important to recognize that the volume of content is huge. Petabytes. It's not a few thousand objects, which is often assumed in studies on caching. And a second characteristic is the popularity of these content items. So there's this notion of a popularity law. Q of n is the probability, no, it's not a probability, it's the probability that a request is for item n is proportional to Q of n. That's what I mean, the request rate Q of n. This popularity is very significant for caching performance. Obviously, if you've got just a few popular objects requested, then you keep them in cache, you get a 100% hit rate. But if the demand is spread over a very large number of contents, then the hit rate is going to be more difficult to attain with a given cache size. So this is typical of measurements which we find on the net. This is just some statistics we obtained fairly inexpertly, probably using the Demonoid tracker, which is a BitTorrent tracker. It allows you to sort the torrents which are currently alive in terms of the number of leeches. And the number of leeches is the measure of the popularity we're using. It does represent the request rate for chunks of these particular torrents. And when you plot the number of leeches against the rank of the object in terms of popularity, so this is the first most popular object, second, and so on, hundredths, 10,000th, 270,000th, then you get this nearly straight line, which is characteristic of a zip flow with a particular exponent alpha, which in this case turned out to be 0.82. People have made measurements of popularity of web documents for 10, 15 years. Typically, the zip flow is a good representation with an alpha in this range. File sharing I've just talked about. UGC is also quite well studied. Video on demand is less well studied as far as I can see. The zip might be a little steeper. I've kept the notion that it might be a little steeper to have a contrast with a general assumption that the popularity is zip 0.8. So this is an assumption. It's something not very accurate. We've got a very imperfect understanding of the popularity, but it's significant. We'll see that the parameter is less than 1 or greater than 1. To evaluate the performance of caching, of the hit rate, we make an assumption, a frequently made assumption in this area, which is the independent reference model. This means that you've got a sequence of requests, and the probability a request is for a given object is always proportional to the same law Q of n, independently of what's happened before and what will happen after. So that's something which is, we'll discuss if it's valid. First of all, I'd like to point out that this assumption is equivalent to assuming arrivals à Poisson, or rather, it's not exactly equivalent. In order to calculate hit rates, we can assume arrivals occur as a Poisson process, independent Poisson process for object n with rate Q of n. This is fairly obvious if you think a little bit about it. It may not be immediately obvious, but it's something I'll use in the model to evaluate hit rates. So is the independent reference model appropriate? It's certainly not true. It's certainly not true that there's a fixed set of content out there. The content is changing all the time. In particular, video on demand with TV, catch-up TV, is changing every week or every few days. What we pretend is that the independent reference model is suitable for modeling performance in a busy period. That means the hit rate in the busiest period of the day, say an hour or 15 minutes or whatever, it's adequate to assume the independent reference model. And this is, if you're used to modeling traffic in the network, this is similar to assuming that traffic is a stationary process, although we know that traffic is varying according to daily patterns and whatever. It's just looking at that busy period, we can assume that we've got this stationarity, which is what I pretend is equivalent, is the equivalent property to the independent reference model. On the other hand, this temporal locality, the fact that content is changing, is certainly important. It's important in being able to estimate the distribution Q of n, or the law Q of n. It's not necessarily distribution. If you make measurements to determine this zip flow over a week, and that week includes changes of content, quite significant changes of content, then the estimation of popularity you obtain may not be applicable to the busy hour. So this is, again, an open area. Most statistics are performed over a long period in order to get some statistically meaningful estimations of rare events, but this has got this problem. There's also the fact that Q of n in a network would typically account for geographical differences, spatial locality, the fact that in Sweden you're going to request programs in Swedish, whereas in France we look at programs in French. That should be taken into account somewhere also. But assuming this, it's a model. We assume we know Q of n, and then we want to evaluate the hit rate. So I'm thinking about least recently used. So the idea is that you've got a cache of finite size. It can contain a certain number of objects. And when a new request arrives, for an object which is not in the cache, you're going to fetch the object from a server and place a copy in the cache. And in placing the copy in the cache, you've got to kick someone else out, another object. So you can do this in different ways. Least recently used means you're kicking out the one which has not been asked for the longest time, not been asked for the longest time. Least frequently used would be if you knew the popularity of the objects, you'd just keep the most popular objects. You might just kick out an object at random. I'm going to study LRU. LFU is optimal, but it's hard to realize because you typically don't know the popularities. There's something which is manifested by the request rates. LRU appears as a reasonable compromise between complexity and performance. The idea is that you're going to link the objects in the list. This is the most recently requested. This is the least recently requested. And if we get a new request for object blue, it goes to the head of the list. It disappears from here, and then the order is changed. If we get a request for object yellow, which is not in the cache, it goes to the head, and we have to kick out the least recently used object green. So the behavior of this process, the identity of every object in this cache and the order in which they're represented in this list is in fact a Markov process, And people have studied its behavior in a stationary sense, the stationary probability. They can write down an expression, they can write down expressions for the generating function of these probabilities, but typically they can only solve them for a very small number of objects, a very small number of objects length of this list. So there have been lots of work on evaluating this probability approximately. And we found in the literature an approximation due to Che, Tung, and Wang. It comes from studies of web caching, and it's proved to be very, very, very useful. So it's under this assumptions I mentioned. These authors introduce a notion of a characteristic time, TC. TC is the time it takes to receive C requests for C different objects. You may request the same object several times within TC, but you receive requests for exactly C objects. So that defines a random variable. We don't necessarily know much about the characteristics of this random variable, but what these authors assume is that for a large system, this time is going to tend to a constant. That TC is not going to be a random variable, it's going to be a deterministic constant, little t of C. If we've got this deterministic case, then the probability of a hit for an object n is going to be the probability that the interarrival between two requests for n is greater than tc, which is given by this 1 minus exponential function. Then you note that c, the cache size, is identically equal to this sum of indicator functions. It's the sum of the object is in the cache. If it's 1, if it's out of the cache, it's 0. But because we keep the cache full, this is an identity. If we take expectations of this identity, we find the expectation of this is just the hit rate. And that's equal to this. So this is an equation for TC, an unknown, which you can solve numerically. So they solve that numerically and then calculate the hit rates. So this is introduced as a kind of heuristic, very simple approximation. It seems to work well. When we looked at it, it works extremely well. So these are simulations as crosses, and the lines are the analytical result from the approximation. And these give the hit rate for the most popular object, the 10th, the 100th, and the 1000th, for a cache size increasing on the x-axis for 10,000 objects. And that's with a zip floor with a parameter of 0.8. If we change the parameter, it's still a perfect fit, almost. And even for a very artificial system where we've got 16 objects only, and they've got a geometric popularity distribution, where there's no large system argument applicable. And yet, the approximation is really very good, you know. So why? We spent quite some time trying to find out why. And this was the object of the paper I almost presented earlier as an ITC paper. I'm just going to sketch the reasons why. It'll go quickly, but it's just to convince you that it's a reasonable approximation. So we assume that at time t0, we've got a request for this object. And we define a process x of t, which is the number of objects, different objects, received between 0 and t. So this evolves, a new object, new object, new object, same object again, it doesn't change, same object, new object, and so on, up to a value c. And when it attains c, we've defined the characteristic time that I introduced earlier. And by their definition, you can understand this inequality. If tc is less than t, then that must mean that x of t is greater than c, and vice versa. So these probabilities are the same. So we can study the distribution of t by studying the distribution of x. The hit rates are truly expressed as an expectation of this exponential function. You can write this as an integral over the distribution of TC and whatever, and that's true. Well, that little animation I forgot about. So the approximation is valid because this x is approximately Gaussian, and I'll just justify that rapidly next. And when you recognize that x is Gaussian, you can introduced the distribution of x in the terms of a complementary error function, and that, again, can be approximated by a step function. So I actually decided to put a few more steps in to make that a bit more explicit. So x is a sum of Bernoulli random variables, 1 or 0, independent Bernoulli random variables. So it's a sum of a typically large number of variables, and therefore it's fairly natural to assume that x will be Gaussian. And we verify by simulation. There are a few central limit theorem results which confirm that this is the case in some limit cases and whatever. But generally it's true. Then we have this expression for h, which can be written this way. This is the deconditioning on the value of capital T. Replace that by the distribution of x, which were the same probabilities, and replace this distribution of x by the complementary error function because it's approximately Gaussian. Then this is a first approximation for h of n. We could use this if this were easy to calculate. This would be an approximation which gives the hit rate directly. However, this is not necessarily easy to do. The approximation follows on approximating the complementary error function. So we have TC is still what it was in the first place. It's the solution to this equation, which happens to be the mean, this thing. And when it's the argument, in fact, of u which annuls this argument. So it's the center point to the complementary error function which does this. We approximate this complementary error function by a step function, which is justified by this little drawing. This is the complementary error function in red. This is a typical shape. With these particular arguments, it's difficult to quantify directly, but we can calculate it. Recognize that that can be approximated by this step function, which goes through this argument, this particular value TC, which is the scalar we had in first place. Then the approximation consists in replacing this integral, this gray beige shape, by the area here. So we subtracting this and adding this, and these are about equal. So, and it's very difficult to prove this to estimate the error and things like that. We didn't succeed in doing that, but just by thinking about cases and how this varies, we're fairly convinced that this is always a good approximation. So this was our conclusion, that the Che approximation is valid, and it's not just a question of large systems and things become constant. We can generalize the Che approximation just by changing that identity. We introduce the size of objects, and we can introduce types of objects, web, files, video, etc. And we can calculate byte hit rates, not just object hit rates. So these are used in the evaluations which I'm going to present. And we can also deal with networks of caches in an approximate way also. The idea is that we've got a very simple network, a low layer of caches, and one big cache. So if you don't get a hit here, you go here. And we want to evaluate the hit rate of the whole network. And the approximation we use is to assume that the independent reference model applies also at the second level, because the requests are coming from a large number of independent processes at the lower level. And each of these processes has got a fairly low traffic stream. Globally, it's behaving again like a Poisson, or can be approximated as if it were Poisson. Therefore, we can calculate a different popularity law, taking account of the hit rates, and then apply the same approximation to calculate the hit rate here and evaluate the overall hit rate, assuming independence, which is again valid when you've got a large number of first level caches. So we use that also later. So what are the characteristics of cache performance using this model and using other models also? These are not necessarily new results for you. You may be aware of this, but it's worth reminding them. First of all, there's a very strong impact to this alpha parameter. It's not a neutral choice whether alpha is 0.8 or 1.2. In particular, the difference between an alpha less than 1 and an alpha greater than 1 is very significant. Here we've got the hit rate expressed as a function of normalized cache size. So we've got the cache size divided by the population. And here we've got a population of 10,000. So this is 1%. If we've only got 1% capacity, then the hit rate with a zip of 0.8 is small, less than 10%. If the zip were 1.2, then we'd have a hit rate rather 60%. So it's very significant, which is unfortunate because the statistics I showed are pretty vague still. We really do need to get a better understanding of that popularity. A second observation is that the population matters. It matters somewhat for the alpha less than 1. In fact, mathematically, you can show that as n tends to infinity, these curves tend to a limit. But the convergence is pretty slow, so that you get a hit rate which is quite different according to the population. So it's significant to account for the population. It's not, you can't just assume infinite and come back from that assumption. If alpha is greater than 1, you get a qualitatively different behavior as a function of the population size. If the population size increases, the hit rate increases. In fact, there's a different limit behavior in this case. The hit rate tends to be a function of C alone and not of the ratio C over n. So it's very significant that it's not just a quantitative difference between the two cases, there's a qualitative difference also. A lot of research I've seen on performance of ICN tends to assume this alpha is greater than 1. And this tends to be an optimistic assumption because you can put a small cache in your routers and have a big impact on the hit rate and therefore on the reduction of traffic which you obtain. But if we had the case which I believe is more appropriate, then we need a bigger cache to achieve, much bigger cache to achieve the same performance. If we apply the Che approximation now to this assumption of mix, which I discussed right at the start, then you get similar curves. This is the, on this case, I allow two possibilities for the zip parameter for video on demand. And that was, I explained why. With a zip of 0.8, we get this continuous blue line. If I put a zip of 1.2 just for the video on demand, then we get the dashed line. So what this shows is that the hit rate is pretty small at a terabyte. It's respectable, let's say 50%, between 10 and 100 terabytes. So these are very big numbers. So if CCN pretends with a single cache to achieve a significant reduction in traffic, you don't need to just replace the FIFO buffer, as Van Jacobson said initially, which is a few gigabytes, by an LRU buffer. You do need something which is bigger, something like an Akamai server or a stack of servers at the side in order to fulfill this requirement of a low hit rate. We could do better if we did more than LRU, if we could approximate LFU by some clever device, then we could gain about a factor of 10 in the size of cache necessary. So that's not insignificant, but it still doesn't save us from the observation that the cache size needs to be big. And I think that's a significant observation for CCN. That's the Jacobson idea where every router's got a cache which is not too big because it's realized in a router is perhaps not feasible. If we look at the hit rates of the different categories of traffic, here we're assuming a zip 0.8 for all. This is for the video on demand. What we see is that the video on demand gets a good hit rate, Remember that this has got a small population, and a population of 1 terabyte only, not 1 petabyte, which is the case for these other 3 categories. The other 3 categories have similar characteristics, despite their different shapes, different size of objects and numbers of objects. It's the catalog size which counts, and its popularity. If we had a more skewed popularity for the video on demand, we get even better performance for the video on demand, but that doesn't change the performance of the others. I cheat, I'm just leaving the same curves, but in fact they don't change. So what does that mean in terms of use of the cache? This is something we can calculate using the same approximation technique. This is the percentage occupation of the cache as a function of its size. So if the size is only 10 gigabytes, this percentage is occupied with web, this percentage with file share, and this with the UGC, and this with video on demand. And as the cache size tends to 1 or 0, these proportions tend to the initial proportions I assumed from the Cisco predictions. But when you get a bigger cache size, so this is a terabyte, 95% of the cache is occupied by these 3 categories. Video on demand occupies 5%, but counts for 85% hit rate. So we've got a cache of a terabyte, which is doing a good job for video on demand and an insufficient job for the others because the hit rate is only 5%, and yet it's polluted at 95% by the other category. I say polluted because it's not really very effective. So this leads you to suggest that maybe you shouldn't be putting all this in the same bag. You shouldn't be putting web, file sharing, UGC in the same cache indiscriminately as you do with video on demand. And yet this is still, I mean, at least in the primitive idea from Van and colleagues, this is the idea. All chunks are created equal unless they've got a TTL, which may mean you don't want to cache them. Now, the last part is about the memory bandwidth trade-off. So the previous part was mainly about one level of caches. It's significant, I believe. It does help understand design choices. But the real criterion for deciding whether one choice is better than another is economic. It's how much it's going to cost. And the idea of an ICN is that the cost is evaluated globally. It's not like IP with CDNs, which have got their own cost equation, their own business model. The operator's got a different, often contradictory business model. Then there's a lot of fighting between the two somewhat. Here we're supposing that we've got a uniform network where caches and bandwidth are paid for by the same entity, more or less. We're going to look at a 2-level hierarchy. So we've got this notion of a lower layer where a symmetric network, this is divided into S sites, S POPs somewhere in a network, each of which has got the same population of users, the same behavior, the same popularity, etc., simplicity. And they're requiring a content bit rate of A bits per second, or gigabits or terabytes bits per second. And the documents are retrieved from the local cache if possible, if not from the second cache, if not from the internet. And if they're retrieved from the internet, this network has to pay something. They have to pay its tier 1 provider for this traffic. We assume that there's an overall hit rate H, in which case the demand which from the internet can be expressed that's S times A times the miss rate, 1 minus H. All this is coming from the internet has got to be paid for. The local hit rate is H of C1, in which case the traffic which has to be carried here is A times 1 minus this hit rate. So the provider is going to have to provide sufficient bandwidth to carry this traffic. So it's not typically a pipe. This is a network. There's routers in the way and whatever. But I'm going to simplify all that. What else? So if I put a smaller cache, I'm going to have more bandwidth to provide, and it's going to cost me less for the memory, but it's going to cost me more for the bandwidth. What's the best compromise as a function of parameters here? So this cost evaluation is very rough. I don't pretend to be really precise by any means. We're forgetting all sorts of known facts. But just to get a handle on the nature of the trade-off. The cost of this network for this type of traffic, which again is 96% of the total traffic, is the cost of the internet coming here, so what you have to pay your tier 1. The cost of the access network here is distributing things to users, and the cost of this bit. I'm going to assume that H is fixed. It's a design parameter. I'm going to assume that the operator wants an overall hit rate of H, say 50%, say 100%, whatever. I also assume that A and S are fixed so that the network access cost is the same. This is the same structure. And I'm going to vary C1, this first cache size, and see what happens to the cost of the remaining part. I'm introducing a very simple cost model, proportional cost model. I'm assuming that to cache content incurs a cost per gigabyte of storage, and it also incurs a cost KT per megabit per second served. So the cost overall is with these factors of proportionality. This is the cost here of serving from the first layer. All data is served from the first layer, even if you have to fetch it from a higher layer. So that's this term. And then the ones which miss here have to be fetched from here, so they incur a new cost. And then the cost of bandwidth, I'm assuming, is again constant multiplied by the traffic. So KB is a cost per megabit per second of network bandwidth, including routers, including taking account of scale economies and whatever. I mean, it's a very simple assumption. Given that, then we can define a notion of a cost variation, which I call delta, depending on C1 and C2, which is the cost of the memory plus the cost of the bandwidth. And I'm subtracting this part because this is constant. So this is the variation as a function of C1 and C2. So I'm going to evaluate this formula for different parameters, assuming some costs. So this is even harder. I mean, try to obtain reasonable estimates of these things. Well, it's difficult because things are not proportional, as I assume, and whatever, but I'm just trying to get, again, order of magnitude estimates. For the memory, I'm looking at the cost Amazon charges for S3. I think it's S3, the cost of memory. That's 10 cents per gigabyte. I looked at the cost of DRAM and things like this, the cost of memory and PCs, amortized on a monthly basis over a certain assumed lifetime. I get something like this, so 15 euro cents per gigabyte. The cost of bandwidth, I found that the cost of the server bandwidth is pretty small compared to the cost of the network bandwidth. There's much more things to provide. And to estimate this cost, then I searched on the net for costs of leased lines and stuff like this. It's very difficult to find. I went to discuss with some old colleagues in Orange, and they said, well, we did a study like this. Sometimes we used €8. I don't know. They didn't say why. I mean, they didn't really know. Even the people in Orange, they don't have all this data. So I took 15 euros. This is like assuming a 50% dimension. I've got a traffic of this. I need twice as much bandwidth in order to carry that, typically. So these are guesstimates. They're not, they're what they are. And this is the kind of result I'm finding. So these summarize the data. I'm assuming this traffic mix that I've introduced, and the zip is 1.2 for the video on demand in this particular case. And the graph shows the delta cost. It happens to be in euros, but it's really hypothetical euros, according to the size of C1, as C1 increases from nothing to the full population size. And I've assumed a hit rate of 1, and assumed that the provider can cache all the content. So this is why all the curves converge to a point here. But let me first say why I've got 3 curves. The red curve is the nominal choice of parameters. And bearing in mind that the choice of these parameters has been rough, to say the least, I'm also plotting what would happen if I were a factor of 10 out on underestimating or on overestimating. If a quick comparison, if I change the zip parameter of video on demand, it changes somewhat, but not very significantly. So that's not really a significant parameter. What we see is, for the nominal case, it will be cheaper if I provided a cache C1, which is somewhere here, like about 1/10 of the entire catalog size, or between 1/10 and 100th. But the cost difference, although this is on a log scale, is not highly significant. I mean, it's maybe 50% of the delta. And that may be significant, but I'm suggesting that it's perhaps not very significant. What is significant is that if the estimations are off, that the traffic is bigger or the bandwidth costs bigger, so that this factor is 10 times bigger, then it's clear that I'm optimally I should provide all the caching at the first layer. All the content is stored in these first layer caches. They're huge, but it's not worth reducing that capacity. I'm only going to increase bandwidth and have to pay more for the bandwidth. If I were on this case, then I certainly wouldn't want to use the layer 1 caches. I'd put all the capacity in the second layer. This is because there's not enough traffic to justify the layer 1 caches. So what's truth? I don't know. If we change the zip parameter, this is again a manifestation of the importance of this parameter. If I have a zip of 1.2, that's steep popularity, then it's certainly always necessary to optimize. I mean, it's optimized to share the caching capacity between the 2 layers. You gain quite a lot. You know, gain a factor of 10. So if popularity is like zip 1.2, certainly the studies which put lots of caches and try to apportion the cache sizes in an optimal way make sense. But what I'd pretend is that if the zip parameter is more like 0.8, then you'd probably not worth it. It's probably much more simple engineering rules you could be applying. This is coming back to that case, and I want to contrast it with this case where I've put a hit rate of 0.5. What we find is that putting a hit rate of 0.1 gives you the good design decisions, at least the criteria which I've been trying to point out, that it doesn't change much. What happens when you put a lower hit rate in, then your cache doesn't need to be bigger than this, but the comparison we made just now still applies. Another significant observation is that if we reduce the population, so we've got a homogeneous catalog of only 1 terabyte, instead of 3 petabytes or whatever I had before, then it's obviously cheaper to put the cache at the lower layer. So this would argue, if my estimations for video on demand were correct, which I had at 1 terabyte, then cache video on demand as low as you can, at least in this particular set of parameters. Don't bother having a 2-level hierarchy. It's not worth it. So just to reinforce those observations, if popularity is zip 0.8, then forgetting about this blip here, which could give you some gain, typically you'd want to be either all at layer 1 or all at layer 2, not doing some clever optimization between the 2. And I'd pretend, again, it's very intuitive, that if it's not clever to distribute cache over 2 layers. It's certainly not clever to distribute cache over multiple layers in the CCN idea where every router has its cache. It's probably not a good idea. On the other hand, if popularity turns out to be like that, if there's some way of forcing popularity to be like that, or just identifying popular objects, then maybe there is scope. So that's very conditional conclusions. And if there's a small catalog, if we split off this video on demand, assuming it's got a large traffic, which is what is the case, in fact, with the estimations we've seen from Cisco, then it's certainly better to look after that on its own. It's got its own economics. It doesn't want to be mixed up with the whole universal content, which might be identified, not identified in a CCN or ICN architecture. So conclusions, I think it's important to try to estimate this memory bandwidth trade-off. It's an essential design criterion, and it's not typically looked at in the literature, I think, not in any clear way. The Che approximation, that was the approximation I presented, it turns out to be a very accurate tool, very versatile tool, because it doesn't need to make any a priori assumptions about the Q of n, the popularity distribution. Significantly, for a huge population of objects, which is, I believe, typical, then you need a huge cache to significantly impact the hit rate. And provide a huge cache might mean that you're not going to put a memory line card in your router, but you're going to put a stack of servers at the side of the router and have some kind of interconnection to get the data, get the content, and probably do more than just getting content, as is the case in CDNs. There's little advantage in distributing cache capacity. It's either all lower layer or all at the higher layer, depending on the traffic, and depending on these largely unknown parameters KB, KM, but that's another question. And it's probably better to distinguish content types and to cache locally traffic like video on demand, if it's got the characteristics which I assume which are not so much the zip parameter as the population size, the catalog size. If the catalog size is not huge, then you can certainly afford to put caches fairly generously at a low level of the network. But of course, the assumed cost model is very rough, and the data is rough also. So kind of navigating in an area where there's lots of uncertainty. This is the best I've been able to do for now. I'm not quite sure which direction to follow now further. So thanks for your attention. That's for good questions.